Can I have a request that we record today's talk?
Yes, sir. The team is already handling that. Yeah.
Okay, thank you.
So good afternoon, Dr. Bhadeshia. Very nice meeting you on this platform. And we all look forward to your lecture. Of course, the department had very many interactions with you. And I think the meeting will start in a formal way. But having seen you just now, I thought I would say hello to you.
Very nice to meet you.
Yeah.
So, you know, we have some time, so carry on discussing what you were discussing before. It's not a problem. Yeah?
Yeah. I would like to add, for the benefit of all those who are present, and also for the benefit of Professor Bhadeshia, if Dr. Jasurya finds it all right, can I make a few observations?
Yeah, please go ahead.
Just now, Professor Mukhopadhyay referred to the two societies. I was also, and how it started earlier. This is the 9th edition. I'm as I observe this, I find it is two competing phases of the student activities in the department. And the equilibrium has reached as a eutectic mixture. And there, the eutectic or eutectodal, whatever way you would like to say this, both phases are important and both coexist. So that's how in retrospect, I observe that the department has come to that equilibrium phase. Both activities of metallurgy society and the Anvesham are taken by the students. I thought I would like to share this observation with you. I hope you will take it in the right spirit.
It's a very good analogy. It's an excellent analogy.
Thank you. Professor Bhadeshia, I think you visited us during our NMD celebrations.
Yes, sir. Yes, sir. It was one of the nicest occasions, and this was before you became an IIT.
Yeah. That was in 2013.
That's right.
Yeah, just at that time we became IIT. And the Indian Institute of Metals, they said that when you will become IIT, we will allow you to organize. So then we claimed that now we are IIT, so please allow. So it's a very mega event, but we could conduct.
Right.
Yeah, and it was nice that at that time you visited Varanasi also.
Yes, it was very. I had never been to that area before, so it was particularly nice. And some of my students came as well.
Yeah. I think now the time is coming very close. Dr. Basu, please go ahead with organizing this, introducing the chairman, and then let the lecture start.
Thank you, Professor Mukhopadhyay. Very good afternoon to you all. I take this privilege to welcome Professor Hari Bhadeshia, who needs no introduction to metallurgical community all over the world, for his lecture on the inaugural occasion of Anvesham 21, which is jointly being organized by Department of Metallurgical Engineering, IIT PHU, and the Metallurgical Society, as well as Indian Institute of Metals. So I convey my personal thanks to Professor Bhadeshia for accepting the invitation to deliver this lecture. And I know he has recently concluded a series of lectures which was organized by Jadavpur University on high entropy materials. So I was not sure that he would be able to make it or not, but he made it. And he has always he has always kept any kind of request that we have made. That is the uh, best part I can think of him. I'm been listening to him since my student days. When he talked about singing still, you must be wondering what is that. But I will not talk about it. What is singing still? That time I was curious, but today I am not curious after listening to him. So thank you, Professor Bhadeshia. And Professor Sastry, all of you know Professor Sastry. He was a professor in our department, and he's a very senior professor. So Professor Sastry has kindly accepted the offer to share the occasion, and so I will not waste any time. I will hand it over to Professor Sastry to chair the session and introduce Professor Bhadeshia and take it forward. Over to Professor Sastry. Thank you.
Yes, thank you, Professor Surya Basu. It gives me great pleasure in formally introducing Professor Hari Bhadeshia. As has already been said, he needs no introduction, but I'm sure there are quite a few young people who are entering into metallurgy field, and this is the right time for them to listen to outstanding speakers like Professor Bhadeshia and outstanding researcher in the area of steels. And before I say something about the formal introduction, those newcomers into the field of metallurgy, either as a student or as a researcher, would always find that the area of steel is all well understood and in quotes, a beaten track. So what is new in this? And this kind of vague ideas and concepts may be there in their mind. And to the surprise of such people, Professor Bhadeshia, through his various models that he is going to present and he is going to discuss, made this field so interesting and so easy to work with, because many of you might realize that there are several components which are added to this kind of a thing. And his outstanding contribution is where he found a simpler solution to find out or arrive at a composition of steel with which you can work, and also a steel which he is going to elaborate that it is the best steel in terms of various aspects which he is going to talk about. So friends, we are very fortunate to have such an eminent speaker, and for the benefit of those who are new to the field, I would like to introduce Professor Hari Bhadeshia. He is the Tata Steel Professor of Metallurgy at the University of Cambridge, UK. His work on solid-state phase transformations has contributed to the invention of new alloys and towards the better processing of existing alloys to achieve unusual properties. This is what I was mentioning in the beginning. His mathematical methods can be used to reduce the vast number of parameters that have to be controlled during the creation and manufacture of new alloys. This is about the design of an alloy you would like to design, produce, and then apply that after, of course, certain testing. He is the author or co-author of more than 650 research papers, 6 books on the subject. He is a fellow of Royal Society, fellow of the Royal Academy of Engineering, the National Academy of Engineering in India, and the American Welding Society. He has been knighted in 2015 as Knight Bachelor in the Queen's 2015 birthday honors for services to science and technology. I am sure most of you would find this is a very brief introduction to such an illustrious person, but without taking much time, from you and Professor Bhadeshia. I would now request Professor Bhadeshia to begin his talk. Professor Bhadeshia.
Thank you very much, Professor Sastry and Basu. And I will start to share my screen. So when I was asked to give this talk, I actually suggested two topics. The first one was the magnetic properties of austenite. And then this talk where I really want you to think differently about steel. So this is the one that was selected by Professor Manna. Now, these are pictures that I took when I visited BHU. So obviously you will recognize your wonderful buildings and campus. But also what interested me very much was these bicycles, because I'm a keen cyclist. You know, I do long distance cycling. And there were tiffins attached to the bicycle. And I love tiffins, the idea of a tiffin to carry the different compartments of food. And my connection with BHU goes further back than this. So for a 3-month period, Professor Manna visited Cambridge to learn about teaching methods. And here he is in our tea room, along with some other colleagues. And his task was to create online teaching materials which do not violate any copyright rules. Okay, so that's quite important. If you want to put your material online, then you must be careful about copyrights and using other people's materials. So he worked very hard during those 3 months, and he produced these resources which are available on the website. First slide. So these have, since he created them, these resources have been the most popular downloads from my website. So if I just show you for the month of May, you know, the top downloads are the documents that Manna created, you know, something of the order of 6,500 documents downloaded per month since he created them. And, you know, to my delight, these have remained as the top downloads ever since they were created. Okay, so there are lots and lots of benefits of these kinds of collaborations across the oceans. Okay, so let me start by commenting a little bit on the title, where I used, you know, changing paradigms. So what does a paradigm mean? Well, a paradigm means a pattern. Okay, so we often hear a certain kind of noise, that steel is under threat, and lightweight materials are competing with steel, and steel content is decreasing in cars. And the reason for these kinds of statements are that people want to emphasize their own research by comparing with steels, and the comparisons that they make are usually not correct. So I intend to show you that far from being under threat, it is actually a very vibrant area of both research and technology. And a very, very simple analysis shows you this, that you know, the annual production of steels is of the order of 2 billion tons, more compared with any other metallic or non-metallic material other than concrete. And not only that, this is the production that was in 1991, and this is what we had in 2020. So it is rising dramatically. And I will point out to you that this kind of an increase in steel consumption is not actually sustainable, but I'll come to that later. Now, why is steel the most successful engineering material? Well, there are 3 basic reasons, okay? The first one is that it is cheap. Compared with some of the other materials that we talk about, it is incredibly cheap. And it has an awful lot of phase transformations, some of which are actually hidden. For example, the magnetic transitions, which have a dramatic influence on the allotropic transitions in iron. So, for example, pure iron starts off as body-centered cubic, then changes into face-centered cubic, and then goes back to body-centered cubic. And the reason for that is the magnetic transitions, which you don't see, influencing the free energies of the parent and product phases in a very large way. So there is no other system where you get this kind of a reversal from BCC to FCC to BCC. What that means is that you can engineer, control the microstructures on a large scale to get the properties that you want. And the third most important thing is that we can make very large structures in a very safe way. So here you have two ships colliding at 90 degrees, and yet neither of them have sunk. And that is because of the design of shipping steels, which are incredibly tough, can be welded, and so on. So we can make very large structures using steels. You cannot do that with any other engineering material. And that is these are the primary reasons why steel is so successful. It is versatile. You can get a strength of only 50 megapascals to something like 3 gigapascals, while maintaining a whole bank of other properties. Okay, now let's look at the statement that the weight of a car has decreased and that the amount of steel that's used in the car has decreased. So this is a Ford Model T, the first mass-produced car. And this young lady was my PhD student. It's Vicky Yardley. And the Model T Ford was the first produced on a production line, and it kind of set the standard for making mass-produced products. And at the time, it had 60% of steel, and it weighed 800 kilograms. Now, this is my small car. It's a Ford Fiesta, and I bought it a few years ago. And it's a Ford Fiesta Eco. It provides 70 miles per gallon of fuel consumption. And it too is approximately 65% steel. And its weight is 1,200 kilograms. Okay. Now, why is the weight 1,200 kilograms? Because the safety features in a modern car mean that you have to tolerate a higher weight. So if I look at the Ford Model T, and let's assume that both cars are using 60% steel, then the absolute weight has increased from 800 kilograms to 1,200 kilograms. So there's 1/3 more steel in one of the most modern cars compared with the Ford Model T, which was many, many decades ago. So the amount of steel being used in cars has not decreased because you simply cannot make good cars without using steel. It really has properties which are astounding. The formability, the weldability, the combination of strength, toughness, and rolling contact fatigue resistance, and so on. So all the bearings, etc., everything in this car is made from steel. And the plastics are there basically in a decorative form, like the dashboard and so forth. So they serve no real structural integrity function. Okay, let's now examine whether the weight of a car is actually decreasing. Well, here are some of the most talked about cars. So this is the Tesla electric electric car, and it weighs 2,500 kilograms. Now remember that the weight of my car is 1,200 kilograms. So this is much, much heavier than the weight of my car. And similarly, we have the Tata Motors Range Rover, which is 2,500 kilograms, even though it is made, the body panels and many components are made from aluminum. So aluminum doesn't help you to reduce the weight to the level of a normal steel car. And this is the Tata Motors Jaguar E-Pace, which is also about 2,500 kilograms. Now, you compare all these cars with the average European car, which weighs 1,415 kilograms. And that weight has increased 12% since 2001, primarily because of the introduction of safety regulations. And the average Indian fleet is only 1,032 kilograms, and an auto rickshaw weighs 500 kilograms. So these cars are actually polluting cars in the sense that they have a very high weight, and therefore necessarily fuel consumption will be higher. And remember, you know, a normal person might weigh something like 70 kilograms. So just imagine transporting one person in something weighing 2,500 kilograms. Now, why do these cars use aluminium in their bodies and so forth, and in the frame of the car? Well, because if they wanted to make a luxury car, they could not make it using steel because the weight would be much higher. Okay, and the problem with using aluminium is that it is not recyclable like steel is. And if you want to find out more about the recyclability, you can find this lecture on my YouTube channel, where an expert from Brunel University looks at the recycling of aluminium in cars. Also notice that these cars are incredibly expensive. Okay, so compared with my car, which you know, when I bought it, cost about 12,000 pounds. These are far more expensive cars. So these are not the cars which you would look for if you want to save the environment or be eco-friendly. Now, I'll come back to this Tesla now. So people think that electric cars are going to save the environment. And, you know, to some extent it is true, because, you know, supposing that we get our electricity from green sources, then of course you can say that you've reduced the pollution by not burning fossil fuels. But the current state of electric cars is not good. And I'll illustrate that by the profits that Tesla made in the last quarter of 2021. Okay, so the total profit was $438 million. And remember, this is one of the most valuable car companies in the world. Okay, and of that, about 300 million went to Elon Musk, which is fine, because, you know, this is his baby. But $101 million of the profit came from Bitcoin sales, nothing to do with the production of a car. And a much bigger component, $500 million, came by selling environmental credits to car manufacturers who are making dirty cars. Okay, now you have to question whether this is an ethical way of trying to solve the environmental problem. So the vast majority of money from making those Teslas came from the sales of environmental credits. Okay, so the net profit was actually much smaller than you might imagine. Now, it is true that you know, if you don't use fossil fuels, then of course you will cut down the CO2 load. But the electricity then must come from green sources. And right now we still burn huge quantities of fossil fuels to generate electricity. So, for example, one of the biggest markets for Teslas is in China. And China has the largest CO2 emissions from electricity production. They have huge numbers of coal-fired power stations. Okay? So electric cars are only a solution if you make them cheap, right? Not very heavy, and you use electricity which comes from green sources. So, and one of the most effective green sources is wind power. So there have been occasions in Britain, long periods, where we have used zero coal because of the largest offshore wind turbine generation facility that has been installed by the UK. And by the next decade, 40% of all electricity for the UK will be generated by wind power. Now, what do we mean by lightweighting? Do we mean that we must have lightweight materials, or should we reduce the absolute weight of a car? I mentioned earlier that an average person might weigh about 70 kilograms, and the car that they are traveling in, if they are rich, would weigh about 2,500 kilograms or more. Well, this is a picture I took in India of an auto rickshaw. And an auto rickshaw has a weight of about 290 kilograms, amazingly environmentally friendly, okay? 290 kilograms. And when you add a few people, its weight can go up to 500 or 600 kilograms. So just look at the ratio of the weight of people to the weight of the actual vehicle. So this is an incredibly environmentally friendly way of transport, even if it has a two-stroke engine and so forth and so on. The fuel consumption from translating a small weight is obviously going to be less than the fuel consumption of translating a very large weight. And here's another picture which I took at the Tata Steel laboratories. This car belongs to Chiradip Ghosh, and its curb weight is 630 kilograms. Okay, and if I exaggerate Chiradip's weight to 170 kilograms, he isn't 170 kilograms, then the total weight would be 800 kilograms. And this is, a really nice concept for weatherproof transport of a whole family of people. Now, there may be many other reasons why these cars have not been successful. But if it was available in the UK, I would buy this car. Okay, it looks beautiful and it has a really nice philosophy behind it. Ratan Tata, when he thought of creating this car, he saw a whole family going on a scooter in heavy rain. Okay, so his idea was to create a nice, cheap car. So this is the perfect solution to lightweighting. That means that we use cars which are actually not heavy. Okay, and the vast majority of journeys that we do are really a small distance, and don't need excessive luxury for small distances. And what I would suggest to Tata is that they should resume production of these cars, but electrify them using lithium-ion batteries rather than lead-acid batteries. And, I think that would make a big difference to the environmental impact of automobiles in India. Now, I mentioned lithium-ion batteries, and, they form the powerhouse for all electric cars, except a very few which are based on a fuel cell concept. And this is an area where metallurgy can contribute enormously, and I'll explain why in the next few slides. So at the moment, very few are recycled, 5% are recycled, and these batteries last for a long time. So we have a long time interval to establish a recycling technology, because in 2030 in the UK, all petrol and diesel cars will be banned, right? They're all new. You won't be able to sell a new petrol or diesel car. And by 2030, it's forecast there will be 30 million electric cars in Europe. So we haven't faced the issue of recycling the lithium-ion batteries as yet, because they are functioning very well. And it will be some time before you end up with a huge pile of lithium-ion batteries. And this is the picture from the Nissan Leaf, which is a smaller and more affordable electric car. And this is the battery infrastructure here. And, you know, the battery, I forget exactly how much it weighs, but it's of the order of 450 kilograms. Now, these are not easy to recycle, okay? And they contain precious commodities which should be recycled. So there are a number of possibilities on how we as metallurgists can contribute to this. So pyrometallurgy, that means you burn the thing and you smelt it, would allow you to recover an alloy of cobalt, iron, copper, and nickel. And then you would have to do some work to separate out the key elements, because they're not present inside the battery as an alloy, but as separate components of the battery, even combined as compounds. And the slag that you produce from pyrometallurgy would contain aluminum, lithium, and manganese, and then you would need to separate those out as well. So a huge amount of science needs to be done, and it needs to be done now in order to prepare for the point where we end up with a large amount of material to recycle. Sorry, I'll just go back. I just need to go back to, yeah. So we need to prepare for the abundance of lithium-ion batteries when electric cars become really prominent. And I would suggest this publication, which is a really, really nice summary of what needs to be done in this area. So, you know, if you have a department of material science, you should have someone working on this area now rather than later. Now, pyrometallurgy means you burn off actually things like the plastics, the electrolytes, and some of the lithium salts, and that's not a good thing. But the process can deal with a variety of battery types. You know, you're just putting these into a smelter, and you know the battery types in the Nissan Leaf are not the same as the batteries in the Tesla or in the Tata Motors cars. Now, the other option is physical separation, where you would actually unassemble the battery and take away the different components, and that is a very, very good way of doing things, because you can then recycle the components themselves. Okay, but these batteries can catch fire, and there might be toxic things inside the battery, and therefore you would need enormous safety infrastructure and a lot of manual labor to do this. But it would be the best way of actually recycling components. Now, hydrometallurgy is when you actually leach out the different parts of the battery. So here, for example, is recovery of lithium and cobalt from a lithium cobalt oxide. And all this needs to be studied. And direct recycling is not just of components, but actually of replacing some things inside the battery and then using the recycled battery for the same purpose. So my suggestion is that this area needs focus. And you know, if there are people who have worked on extraction metallurgy or chemical metallurgy or corrosion, they would have all the skills that you need to do the research and establish a center for recycling of lithium-ion batteries. Now, of course, if you build the right sort of infrastructure in a city, for example, cycle paths which are safe and so on, then it's a very good way to use bicycles and therefore not only get healthy, but save fossil fuel. So here, for example, is Nirupam Chakrabarti, who you might know from IIT Kharagpur, and he's soon going to go to the Czech Republic for 2 years to work at a university there. And you can see the quality of the cycle path here, okay? It's separated from the road, and you can safely cycle without colliding with heavy lorries, etc. So supposing you took Jamshedpur, right? And from the center of Jamshedpur, you establish cycle paths and you banned cars, individual cars, as opposed to public transport. Then you could slowly create the infrastructure where people start to cycle to work rather than go by car or by bus. And of course, school transportation can also involve cycling. So here is a more complicated bicycle where you see everybody on this is cycling. Okay? And this is an image I took in Berlin. Of course, they are having a lot of fun by doing this collectively. But, you know, if you're transporting children to school, they could all be cycling. So these are ideas which break the paradigm, okay? The pattern in which we have come to live, where, you know, for short journeys, we take a car journey rather than walk or cycle. I now want to move into technology and how we can break our conventional thinking in technology as well. And once again, you know, Elon Musk features, because this is the Starship that he's building. It's called SpaceX, and ultimately it will be designed to take people to Mars. But in the meantime, you know, if you want to establish a moon base or take heavy loads into space and then recover your launch vehicle, this is the Starship, which already has performed, okay? And it has transferred people and cargo, not to the moon, but to the space station. So we can have long distance space travel. Now, originally, the idea was to make this from a composite, a carbon fiber composite, but very quickly they realized that's not a good solution. Because, for example, in Mars, there is the density of the atmosphere is less than that on Earth. So in order for a rocket to enter the atmosphere, it has to go at a glancing angle, which will cause a lot of heat. And composites will not survive that. You know, they are basically bonded together carbon fibers. And similarly, aluminium would not survive that. You know, as you know, aluminium is light, but it is also precipitation hardened or some other factor to harden it. And if you heat it up, then you're going to lose its metallurgical integrity. So this is actually made from stainless steel. Okay, this rocket is made from stainless steel, welded together. And you know, if before Elon Musk you ask somebody whether you would have a rocket which is made from steel, they would have, a material scientist in particular would have said, you know, you are talking nonsense because you have to use a lightweight material. Steel is strong, and therefore you can make it lightweight by using less of it. So this is his reusable interplanetary vehicle. He calls it the Starship. And, you know, it's designed to cope with freezing and scorching temperatures. And Mars has a thin atmosphere. So you have to enter at a glancing angle to ensure that you have sufficient drag. And of course, that leads to heat. And even with the steel, there is a liquid methane pump under the surface of the Starship to cool the steel. So none of these materials can actually cope, right? Aluminium and composite. And furthermore, they are more expensive, and composite certainly is not recyclable. And that's one of the problems that needs to be faced when it comes to wind turbines, because the blades of a wind turbine are made from composite. What do you do with that after their finished service? So steel has no challenges, but it does lead to CO2 production in a big way, all right? And this kind of an increase in steel consumption is not sustainable if you want to avoid the worst effects of climate change, which will have the greatest impact on the poorest nations of the world, who can least mitigate the effects of climate change. Okay, so this kind of consumption is indecent. We need to reduce the steel consumption of steel. And just to give you an example of the construction industry, this is a massive steel beam which uses 1,300 kilograms per meter, 1,300 kilograms per meter of steel. And this is used for making very tall buildings, extremely tall buildings. Now, why do we need extremely tall buildings? We don't need them. People are constructing tall buildings just out of fashion. We want the tallest building in the world, and then somebody else makes an even taller building, and so on. And those buildings also require huge concrete foundation, which is another material which is, has a heavy CO2 burden. So I'm going to show you an example of how to reduce steel consumption without losing the capability of having a high quality life. Okay, because steel improves the quality of life in so many ways that we are not going to stop using it. But if we can make better use of the steel, then we can use less quantities of steel. And this is actual, I'm going to show you actual data from the construction of a building which uses a better steel than the normal steel and yet manages to reduce the overall cost. So this is from work done by CBMM in Brazil. And this is the final building that was constructed. And the building is constructed on a steel frame, which has these three types of girders. This and this use a high quality, when I mean high quality, I mean a stronger microalloyed steel. Okay, so it is more expensive than a normal steel. And this is your normal steel, which they use for the braces here. And the building exists, okay? I have seen it. So by using the stronger microalloyed steel, which is represented in green here, you actually reduce the size of the beams that you need to use. Okay, so this is engineering design. You give the engineer parameters that, look, this steel is better than this, then they can redesign your building to cope with a higher strength and a smaller amount of steel. So this beam uses 22% less steel, or in the whole building construction, 22% less steel was used. And even though the microalloy steel is more expensive than the ordinary steel, there is a 17% cost saving because you are using less steel. There's a 1.8 gigajoules of energy saving and 128 gigagrams of carbon dioxide saved as a consequence. So, if you combine engineering design with using a better steel, and we have the technology for better steels, and, if even better steels need to be created, we can do that, I believe. Then you can actually reduce the consumption of steel. So instead of 2 billion tons, if you had a 20% reduction in the amount of steel used, that would immediately drop to 1.6 billion tons. That's a 400 million tons saving of steel and the associated carbon dioxide, which is about 3 tons per ton of steel. So you're saving 1,200 billion tons of CO2 if you actually use better steel. Now, I mentioned engineering design because, this whole subject is not about a material alone, but about a whole system. And I'm going to show you a little video recording now of a different kind of a beam design for construction. Now, here is a beam which is asymmetrical. The length at the top is different from the length at the bottom. And the idea here is that instead of putting the floor on the top, you would insert the floor through the sides. And in that way, you avoid the need to fire protect the web region. And fire protection is extremely costly because you actually have to enable the building to survive for more than 1 hour in a fire scenario. The additional advantage is that you save in terms of the height of the buildings. So for a normal building, which would be 11 stories high using I-beams, the same height of floors could be achieved by using an asymmetrical beam with the floors slotted in to the central region of this beam. So here is that beam again. And the idea is that for the same height of a building, you can have more floors. Plus, you don't need any fire protection in this region because you are slotting the floors in, and the services can go through the floors themselves. So it's a very neat and tidy solution. And this is a commercially available. And this whole section is actually rolled out of solid steel slabs, hot rolled out of solid steel slabs. So there's no welding involved here. Okay, now this is a building in Taiwan that I was fortunate to be able to visit when it was under construction. So here I am, and this is Professor J.R. Yang, who was one of my first PhD students and now is a big professor at the Taiwan National University, and Professor C.H. Young, who is in the construction department of another university in Taiwan, and he was also in Cambridge at one time. And these are dear young students, okay? So because I knew them, I was able to go into this building, which is 101 stories high, during the construction stage. Now, there is a problem with tall buildings, okay? And what I want to show you is additive manufacturing at its best, okay? So you must have heard a lot about additive manufacturing, but I'm going to show you examples of additive manufacturing on a huge scale in the context of this building and in another context. So the problem with tall buildings is that they are subject to wind forces, and in the Taiwan building also to earthquakes. So if you just take the elastic deflection of the structure, which is made from steel, okay, then that accumulates as you go up the building. And, you know, if you do nothing, then you would have a deflection of 1 meter due to wind at the very top. And that is, you can't actually use a building like that. And just to illustrate this, I was also in a building in Moscow on the 60th floor having dinner, and there was a chandelier at the top for the light, and it was a bad weather day. So this movie shows how the chandelier is vibrating as a consequence of wind on the 60th floor of a building in Moscow. So these are not 1 meter because this is only roughly 60 floors high. And the wind wasn't as bad as the worst case scenario. But you can see that just elastic deflections cause the building to move, to vibrate effectively at a low frequency. So how do we cope with this? Okay. Well, in the building in Taiwan, there's an ingenious structure. Okay. So there is this steel ball which weighs something like 900 tons, which is suspended from the 92nd floor, okay, and it's connected to dampers. So this is known as a tuned damper. That means the mass of the ball, etc., is designed to compensate for the forces due to wind and earthquake. And this is actually the steel ball, which is made from steel plate cut into circular sections and joined together. So this is a 900-ton object, which is additively manufactured layer by layer by putting the different sections of steel on top of each other, welding them and making a ball. Now, this story has become a huge tourist attraction. This picture I took when the building was under construction, but they have since then painted this golden. Here you are. And there's a gallery where visitors can come and observe this. So these are incredibly strong steel ropes, something of the order of 2 gigapascals in strength, made from drawn perlite. And this is your additively manufactured massive steel ball, which is connected at the bottom to these dampers which contain silicon oil. And the whole thing is tuned to the required resonance frequency of the building. Okay. So this is one of the largest additively manufactured components and made in metal. And by the simple technology that you take, slabs of steel in the correct shape and you stack them up, and that really is the concept of additive manufacturing. And in the same building, they've made some concrete here, which has a density of just 0.9, less than that of water, by mixing concrete and porous clay from the bottom of a dam. So these features would not be possible if the density was of normal concrete. Okay, and that was this has been designed by Professor C.H. Young, who I mentioned earlier. So I'm going to show you now another example of additive manufacturing of steel, again on a grand scale. Okay, so you don't need to think about additive manufacturing as just a tiny component being made by putting a laser or a welding wire. You can make huge objects by additive manufacturing. So this is a steam turbine, and it is much longer than illustrated in this image. And this is Tracy Cool, who was my PhD student. Now, when you make large objects, they will contain chemical segregation because you cast them, and there's no way in which you can get rid of long-range segregation by homogenization. So if you look at this ingot, there's quite a lot of segregation. The scale here is 0.5 meter. Now, this is also a very large component, and you can see that there is almost no segregation. Now, how has this been made? Well, you continuously cast the steel as normal, and you cut it up into chunks. You stack the chunks up in a vacuum, and you then make welds between the plates. You then forge them together, okay, and rotate. The forging can even create circular components. And this is our rotor, okay? So by doing this, you cut down any effects of long-range segregation. And the pictures that follow are real pictures of massive components made in this way to avoid segregation, okay? So this is at Shenyang, the Institute for Metals Research in Shenyang. Look at the scale here, okay? And I deliberately took pictures with people so that you can see the scale of the structure that is made by stacking these plates together, joining them up, and then forging them into shape. Just 1 second, I need to... That's the danger of working from home, that someone rings the bell. But my point is, if you use your imagination to solve a problem, then you can create radical technologies which will change the way in which we work. And this is a steel object with the problem of chemical segregation completely removed. I'm going to show you another example where imagination features heavily. So there's a class of steels known as the TWIP steels. That means twinning-induced plasticity steels. And they have remarkable properties. They start off quite weak, but a huge amount of elongation and a work hardening rate, which means that you don't get plastic instabilities, and therefore fracture occurs at a very large strain. And the reason for this sort of behavior is that, just 1 second. Hello? Yeah, I'm sorry, I'm giving a lecture at the moment. Yeah, but if you want to look around, yeah, because you said 1 o'clock, didn't you? Okay. Yeah. Yeah. How big a table? Yeah. There you go. Okay, no problem. Okay. Yeah. No problem. Thank you very much. I'm giving a lecture at the moment. Okay. Okay. My apologies once again. I was talking about TWIP, twinning-induced plasticity steels, and the reason why we get this nice work hardening, which delays plastic instability, is that as you deform, you get mechanical twinning of the type illustrated here. And that mechanical twinning divides up the parent grains into ever smaller grains. So effectively, that gives you work hardening because you need to think about this like a dynamic hole patch effect, where you're reducing the grain size by partitioning the grain with these mechanical twins. So on the face of it, it has excellent properties. Okay, now these are the sort of components that you would use in a car for safety. So if you have, say, a head-on accident, then these objects will deform, and in doing so, they will absorb energy and therefore, to some extent protect the passenger compartment. And the one on this side is made from steel, and on this side, it's a composite material where energy absorption occurs by the tearing apart of the composite. So the TWIP steel that I showed in the previous slide might be suitable for this application. And this is an example of a TWIP steel which has been tested in the same sort of scenario that I showed in the movie. Now, there is a problem here which Wolfgang Black identified, and that is that, the TWIP steel only absorbs sufficient energy after a large amount of strain. And a large amount of strain only happens in the most bent regions here. Whereas, if you had a material which started off quite strong and had a stress strain curve like this, then it would absorb much more energy. So it turns out that it's not actually suitable for this crash resistant application, simply because it starts off quite weak and then reaches a strength of 1.2 gigapascals. And the way in which this component is designed means that you do not get uniform deformation. So much of this remains at a low strain. So do you abandon this idea? Well, this work that I'm going to show you is done in Germany, and it's incredibly innovative. So what they did is design a method so that you get uniform deformation. Okay, so these objects here are made from TWIP steel. They are cylinders of TWIP steel, and they're designed so that in a crash they would become extruded. Okay, so that extrusion gives you uniform deformation throughout the material, and you get much better energy absorption. So I'm going to show you a movie and acknowledge the German rail industry for this. So this is how the TWIP steel is being used to absorb energy in a crash-resistant scenario. So during that crash, the TWIP steel is being extruded, and therefore you are using the material in such a way that you get uniform deformation. And I thought this was an amazingly clever way of using the material instead of abandoning it for crash resistance. So in today's talk, I have tried very hard to show you that, first of all, steel has no challenges at all, okay? But there is no doubt that we need to reduce consumption. And to a large extent, this can be done by a better use of steels rather than, for example, by carbon capture, which uses energy itself. And there's no possibility of producing all the steels that we use using hydrogen, because the hydrogen would have to be generated from green electricity. And I think we need legislation to increase the cost of steels. Okay? And I have a number of ideas on how you could do that as an individual country or as an international collaboration. You know, one simple idea is that if you buy something, then and doesn't matter which country it comes from, then there is a tax associated with it, which depends on the content of steel. Because as I said to you, steel has no challengers. It is such a successful material that people want to use more and more and more. So we need to do something about this and bring back steel production to about 800 million tons per annum. But you know, the sort of ideas that I've tried to explain to you are about thinking in a different way. For example, with additive manufacturing, you could do additive manufacturing by taking sheets and then stacking them up and joining them together and forging them and so on, rather than just by depositing it from a powder, etc. And you can create your own paths in research and focus on a technological need, because that tells you that there is a complicated path you need to follow in your work. And new industries, the particular one I think is very promising is on the recycling of lithium-ion batteries. So I will stop now, and I'll be very happy to answer questions. Okay, now I just need to discover a way of stopping to share the screen. Maybe the controller can help me. Okay, got it.
Yeah. Thank you very much, Professor Bhadeshia. Before I open the talk for discussion or question answers, I would like to make a few observations, not repeat all that you have said, but the links that you had established with our department, and where Dr. Rampad Manna is continuing to work on similar ideas. So that's one thing. And you referred to recycling, and at the end also you were referring to recycling. We have one younger colleague in the department, Professor K.K. Singh, who works on recycling, and he was recycling or recovering precious metals from printed circuits, boards, and so on. But I'm sure he can take up this kind of work. And that would definitely add to what our department has a motto. I don't know whether you had a chance to see it any time. We have a motto: let's create technologies for tomorrow, or let us build technologies for tomorrow. And a department like this, and with guidance or help with ideas from people like you, I'm sure the colleagues here can take up that. What it's for the benefit of the younger students, I would like to say that Professor Bhadeshia's lecture has been an integrated approach. Many of us, you might have seen during our work, concentrate on one idea and try to sell that idea that this is the best. be it nanotechnology, be it whatever it may be. But he has shown you the importance of having an integrated approach. And for the senior colleagues for research ideas, he has given enough number of them. And for the young students, he has opened up an area where challenges are very intriguing situations can be there in technology, and how you can choose a career path in that. And so with these few words, I would now request the young participants particularly to participate in the discussion. Yes.
Thank you. So I don't know how this works. Does the person need permission? There is someone called KS who has raised their hand.
Yeah, somebody on the department side said that they will help me in connecting that. I'm not coordinating that. Jasurya, can...
Yeah, can I ask, sir?
Yes.
Myself.
Yeah.
Yeah. So it's really very interesting lecture, sir. Very inspiring. And though it was centered around steel, but I picked the recycling part. Professor Shastri has already told you about myself. I'm working in the area of recycling of electronic waste. And recently I completed one project in collaboration with Professor Jason of the University of Edinburgh, and that was under UCARI scheme. And we successfully collaborated. Professor Jason had experience of recovering gold from synthetic solution, and I joined with him with my successful research on delamination of printed circuit boards, so exposed metallic values. And all together, we both successfully recovered more than 97% of gold, similarly 95% copper and nickel. So the project finally completed with 4 metals recovery. Then after that, we got GCRF project, EPSRC, again from UK. We have 2 collaborators, Edinburgh University and Dundee University. And from India, my university is there, and one National Institute of Design is also involved into that. So in that, we are making some we are find application, direct application from this waste. So we are targeting the jewelry industry, but unfortunately due to COVID-19, it is on hold. Okay, so now I'm interested to know from you, sir, because this is very interesting for us, and already we have started work on this lithium-ion battery recycling. 2 tech students current year, they could not perform the experiments, but cobalt as well as lithium, both recovery was our target, and we are really very much interested. So now my question, rather I wish suggestion from you, how to carry out, how to go ahead in this pandemic, because everything is stuck, and in spite of our enthusiasm and students' availability up to some extent, we are not moving forward. So your suggestion and what to do, sir, out of your vast experience.
I think the most important thing is that you protect yourself for the moment. Yeah, for the moment, everyone has to. Doesn't matter what our research priorities are, etc. If you don't live, then you can't do anything. Okay. So in our university, for example, we have done completely online teaching for 18 months now, including examinations and so on. We allow 25% occupation in the department for research students, isolated research students. So only one person can be in the lab with many precautions, you know. So the most important thing is to safeguard life at the moment. And then, you know, for the moment, you could write an extensive literature review, for example, on lithium-ion battery recycling, just to gather all that information, and that you can publish. If you do a really good job, there's plenty of opportunity to publish, no matter how long your review is. You can put in Progress in Material Science. I've published 200 pages, or international materials reviews and so on. So in any research, the first step is you survey what has been done, and that would be a good time to do. Now would be a good time to do that sort of work. And of course, you can look at theory as well. So if you can find some electrochemical theory which will help you in the process, that would be good as well. But we have to live with this current nightmare.
True.
Thank you, Professor Bhadeshia. Thank you so much.
Professor Mukhopadhyay?
It was, as usual, very nice presentation, and it's always a learning experience from your lecture, something or other. So I would like to ask one general question and one very specific question. The general question is, what about the steel foam? From a stiffness point of view, is there any kind of potential, according to your perception, the steel foam? It's clear that the steel foam means that what is the air bubble inside the solid structure, where the stiffness of the steel may be very high. That is number one. And number two, as you have given series of lecture of high entropy alloy, people do talk about high entropy steel, especially one group. And recently we are also trying to tackle some work on high entropy steel and taking expertise of Dr. Manna as well. That iron, nickel, chromium is common, and then put manganese and aluminium, just to put some amount of density, and then whether kind of microstructure you get, B2 means ordered BCC and disordered BCC, just like very similar to superalloy kind of structure, whether that can withstand very high temperature kind of application. So I would like to draw up your attention only these 2 points. One is steel foam, another is high entropy steel, where we can try to achieve the low density aspect, and at the same time microstructural design should be such that analogous to superalloy. These two are my general, but if the time permits, I have another specific question.
Yeah. So regarding steel foam as a method of getting rigidity, so the best way to get a rigid structure using steel is engineering design. So a simple example is your corrugated roof, and so on. And steel foam is obviously you have to think of an application, and if you think of an application, then you need more than just the rigidity. So I would say, and of course I haven't done the work, I would say that the material will be expensive, and furthermore, it will not have good structural integrity. So the reason why I say this is because I have actually looked at a project being done in Tata Steel, where we can produce steel foam from waste product, and they have the technology. But the properties that are being looked at are different from rigidity or structural properties. So you can fire the imagination, but start with an application and see whether you can achieve those properties. And with respect to the metallic compounds that you were talking about, the beta and beta prime superalloy type of structure, I think that is possible. Once again, we need to look at components. So we designed, for example, an aircraft engine shaft, which is now in the process of, it is in a test engine. that shaft has the beta prime precipitation in it, but it is ferritic. Yeah, ferritic. And it's designed for creep resistance, toughness, and so on. The volume fractions are much smaller than you might have in a nickel-based parallel, example of gamma prime, because we're looking at properties at around 400 degrees centigrade. The shaft itself doesn't get much higher than 400. But I think it precipitates is a slightly neglected area.
Okay. Can I ask another question? Technical question, yeah. You were talking about the twist steel, twin-induced that plasticity. This particular steel, as you were also saying, that dynamic hull patch kind of property one can achieve it. Now, what is that fundamental mechanism because of which there is a possibility? Because these are all PCC or FCC kind of structure. And what is that driving force that you get twins so often during this deformation? That is my point, that whether really we get a deformation twin, or if we do the heat treatment, then we may get back to the annealing twin, or both do it mechanical and annealing twin both. So if you can clarify on this issue. Yeah.
So these are definitely mechanical twins. Before deformation, you don't see them, and after deformation, you see them, and you can even measure the shape change, the actual shear. So the simple explanation is, as you add manganese to iron, the stacking fault energy changes. So initially, you start to get epsilon martensite. If it's austenitic, you start to get hexagonal martensite, HCPI. And at some point, the fault energy becomes such that that transformation disappears. And no matter how much you deform, the twip steel stays austenitic, but it deforms by mechanical twinning.
Yeah. So it will lead some kind of brittleness also?
No, it's extremely ductile, simply because these twins are very, very thin, and their biggest effect is to divide the austenite into smaller and smaller grain size. So you are introducing a work hardening capacity, and that delays the plastic instability that you get during tensile testing to a much longer strain.
So essentially, manganese is the responsible element, I guess.
Yeah. Yeah.
Okay. Thank you. Thank you very much.
There's someone called S. Saurabh Pandey.
Sir, first of all, good afternoon, sir. Sir, I want to ask that, sir, since 2004, the discovery of the wonder material, so can you think that in future graphene can replace steel?
So actually on my website, there are videos explaining that and publications as well. So this is a complete nonsense. So there is a fundamental thermodynamic calculation that you can do, that as you increase the size of a crystal, for example, a crystal of iron, okay, from less than a micrometer in size, it has a strength of something like 12 gigapascals. And as you increase the size, thermodynamics tells you that you will have an equilibrium number of defects, so the strength collapses. And this work is before 1950, 56. We know that when you measure the strength of a very small particle, it will not be the same as the strength of a particle which is 1 millimeter in size. And many years ago, I wrote a paper on carbon nanotubes to show that it's complete nonsense to say that we'll be able to make ropes with a strength of 130 gigapascals for exactly the same reason. And I sent the paper to NASA, actually, because they were thinking about the space elevator concept. So basic thermodynamics tells you that if you rely on strength, rely on perfection for strength, strength simply disappears as soon as your particle or the number of atoms in your object becomes larger. And exactly the same applies to graphene. And I presented this talk at a graphene conference, actually. So it's on my website. So, the scientists have unfortunately focused on publicity more than on the science, because this story is known from before 1950, that you cannot maintain perfection in a crystal as the crystal becomes larger. And of course, the reason why they're doing this is to impress funding authorities who don't understand science. Okay, but if you do work in an honest way, then you will achieve what you claim at the beginning of the project, or you might achieve. But it's physically impossible to get graphene to be stronger than steel once you get to more than 2 millimeters in size.
Sir, I want to ask one more question, sir.
Mm-hmm. Yeah.
Sir, in your last slide, you have said that steel have no challenges, and in future we have to increase its cost. Sir, how we can increase its cost? Then no one will buy it, sir, these products.
Yeah, but that's the whole point. We don't want people to buy too much steel. Okay, so we want to make the same profit, otherwise the companies won't survive. Okay, so you have to put a tax on the use of steel, just like you have a tax. In Britain, we pay huge tax on petrol. Every time we buy petrol, there's a very large tax, far more than the cost of petrol. And that means a big drive to increase fuel efficiency. Okay? That tax has existed for 40 years. So 80% of the cost that we pay for petrol is tax. So we could do a similar thing, that whether the goods are imported or manufactured locally, we charge according to the steel content and pass money on to the steel producers to make better steel, which can be used in smaller quantities.
Yeah.
The solution is there. It's almost straightforward. But we need to have the courage to implement.
And sir,
Go ahead.
Sir, what is the future of electric cars, sir? In coming 10 years, the future of electric car, will it replace all the petrol and diesel running cars or not, sir?
I have no doubt that it is the right way to go. Okay, but we need to make small and cheap electric cars. At the moment, the focus is on things like Teslas and so on, which are ridiculously expensive.
Any others? I think more number of students should take interest in. This is a very nice opportunity for you, for all of you.
Sir.
Yeah.
Sir, can I ask one more question, sir?
Yes, you can.
Yes, sir. In steel, which are the areas you think still needs lots of research, sir, in coming years?
So my aim in doing this lecture is for you to come up with totally different kinds of ideas. Yes, so I've given you examples of totally different kind of ideas. If I could actually predict the future, then I would be doing that myself. Okay, so I want you to actually come up with ideas on research.
So there are 5 hands raised.
Yes.
Starting from Jayasuriya Basu to...
Jayasuriya Basu, yeah.
Okay. Go ahead.
Thank you. Actually, sir, this is a very nice, stimulating lecture. What I'd like to know, it is regarding the 12 steel. So, so far I know that interpenetrating twins in steels were reported by Jack Christians and Basinski way back in 1958-60. But they never mentioned in those papers 12 steels and all this. And now we understand that these twins are mostly deformation twins, of mostly compound type deformation twins. And by changing the deformation that you can apply to the material, you can change the alignment of the twins also. So is there any solid theoretical approach which will help you in predicting beforehand that this is how the steel should be designed and this is how the deformation should be imported to the steel, so that you can align those twins in such a way that you can maximize the properties of the steel? I am not really aware of this. So if you could really guide me on that.
It's a very, very good question. The twip steels didn't exist when Jack Christian was doing his work, and when Mahajan and Christian wrote that review in Progress in Material Science. But the concept of mechanical twinning, of course, was dealt with incredibly nicely in that review article that they wrote. Yeah. Now, it is actually a physical deformation, and it's exactly like martensitic transformation, where you get a change in the case of martensite, you get a change in crystal structure, but also it's a physical deformation. Okay. Now, the twinning shear is much larger than in martensite. It's about 1 over square root of 2, whereas in martensite it's about 0.26. So there is no doubt that when you pull the material, the twins that should form are those which relieve the stress. Okay, so you will tend to get a selection of twins, but bear in mind that this is a polycrystalline material. If you were working on a single crystal, then that would get aligned twins. Yeah, but in a polycrystalline material, to maintain integrity, you need 5 different deformation systems to operate at the same time. So it's unlikely that you get a great deal of alignment by applying stress, but you might get some selection.
So you mean to say as you cross the grain boundary, the twin alignments will differ, even though there might be the angular relationship between 2 consecutive twins might remain the same.
Yes.
And the second question is, are these twins still mostly compound twin, or there are examples of type 1 or type 2 twins also?
No, I think the symmetry of the FCC lattice is such that the easiest twinning mode is favored.
Okay.
So you do find type 2 twins in martensite, for example, in the copper gold alloys and so on. Yeah.
Yes, in that case, one variant has to be irrational variant.
Okay.
Yeah, so I do not know really in steel that irrational variants you can get.
No, yeah.
All right, thank you, sir.
Okay.
Madhumani or someone is raising a hand.
Ritesh Tandon.
There is somebody by name Madhumani.
Hello,
Yep.
sir.
Hello.
Hello, this is Madhumanti Bhattacharya. I am an assistant professor from IIT Dhanbad.
Okay.
I have a very basic question, somewhat related to what Professor Mukhopadhyay asked. We have seen that when we add manganese to twip steel, the stacking fault energy decreases. Similarly, the effect is noticed in case of the nickel addition.
Right.
So what is the physics behind having manganese lowering the stacking fault energy of the FCC matrix?
Right.
What do these 2 particular elements do in case of austenite matrix?
Mm-hmm. So that's a very good question, and it's a question which has an endless answer. Okay. so the reason is as follows. So I could tell you, that manganese lowers the free energy of the HCP ion relative to FCC. But then you can ask, okay, why does it lower the energy of HCP ion relative to FCC? So you could do some first principles calculations, but they still don't give you the sort of insight that we get from ordinary discussion on why it actually does lower. All I can say is that everything indicates that it stabilizes the HCP structure, but not the electron theory or something behind that, because you can keep on asking the question of why that happens, And the normal way we rationalize the effect of alloying elements is the free energy of
Okay.
the two phases.
Okay. My other question will be, in case of TWIP steel, we talk about deformation twins. Also, when we anneal the structure, we used to have numerous annealing twins in the microstructure. Is it possible to use those twins kind of like pinning the migrating grain boundaries?
So certainly the boundary between an annealing twin and a deformation twin is essentially identical. It's a very coherent boundary. So it would present the same sort of barriers as a mechanical twin. So, the crystallography, if you ignore the deformation, is identical.
Yes. So when it intersects, so if we consider an austenite grain, when it intersects an annealing twin, or it has an annealing twin inside it, can we just consider the part of the annealing twin that it has an intercept on the austenite grain boundary, the random boundary? It
Right.
somehow gets pinned.
So excuse me for just 30 seconds. Okay. Thank you very much. Thank you. Oh, you need a signature? Sorry. No problem. Okay. It's fine. Excellent. Thank you. Yeah. So I have an engineer who's looking at some part of my house, and that's the reason why we have these interruptions. Okay.
All right.
Can you just repeat the last question?
Yeah, so it was like we were talking about dynamic hole pitch through deformation twins. So
Right.
we can kind of use the deformation twinning as a grain refining method during the deformation.
Absolutely.
Similarly, when we anneal the structure, the annealing twins intersecting the austenite grain boundaries can act as like a zarpinning kind of thing.
Well, the only problem is that when you talk about a grain boundary and the movement of a grain boundary, that will involve diffusion. Okay. And that diffusion, the boundaries are not much of a barrier during recrystallization. Grain boundaries and twin boundaries are not much of a barrier because diffusion happens. If you had particles which don't dissolve during the annealing, then they basically cause the boundaries to bow. So it's not likely, although an experiment would be nice, that annealing twins themselves act as barriers.
Okay. Okay. And if time permits, can I ask one more question?
Yes.
Like transparent aluminum, is it possible to think of transparent steel?
It's a very good question. I can answer that very well because sometimes ago, just for fun, I wrote a little article called Transparent Steel. And, there is the reason why a metal is not transparent is because we have these electron energy levels, and it's very easy for an electron to be promoted to another level. So when light falls, the light is absorbed by this process. So in order to make it transparent, you would need to make it an insulator. In other words, put a band gap. Okay. So that can happen if your ion particle gets to less than about 50 nanometers, okay, or 5 nanometers, sorry. And that is predicted by the Mott metal insulator transition. Now, the problem is 5 nanometers. So the wavelength of light is 10 times, 100 times bigger than that. So what does then transparency mean? Because if you actually put the particles together to make a sheet, then it will become a metal again and become opaque. So it's probably fundamentally impossible to do.
Okay. Okay, thank you, Professor Bhadeshia.
Okay.
There is one, yeah. There is one Saptarshi who has been raising.
Okay.
Yeah. Good afternoon, Professor. I'm a
Hello.
research student of Professor N.K. Mukhopadhyay and Dr. Joysurya Basu in the
Mhm.
Department of Metallurgical Engineering, ITBHU. So actually, I read a paper in the recent past. I don't remember the name of the authors at the moment, but they claim that the epsilon carbide that precipitates out during the first stage of tempering in martensitic steels is actually an HP3 thermal omega type of structure. So my question is, in the from the point of view of physical metallurgy or research in the fundamental physical metallurgy of steels, how exhausted or unexplored is the field studied in 2021?
Yeah. So this omega transformation that you talked about is a misinterpretation of the electron diffraction patterns. So what happens is that when you have an inclined interface, you are actually getting double diffraction, and there are periodically over the years you will get papers which think that the double diffraction is because of an omega transformation. And in my latest book, which is called The Theory of Transformations in Steels, I don't know if you can see it or not. I have a section
Yes,
on the illusory omega transformation to point out the error. And I pointed that out in 1987, but every time someone buys a new electron microscope and uses it, they misinterpret the double diffraction to imply an omega transformation. And I think the most recent such paper was from China. Yeah.
Yes, sir, exactly.
Mm.
Okay. Thank you. Thank you so much, sir.
Okay.
Okay. Any other?
Prashant Kesharwani. Yeah.
So Jayasuriya wants to say something?
Good afternoon, Professor. Yeah, as you have discussed about the additive manufactured trip steel. So, sir, do you think there is a directional mechanical property of that steel in along the parallel direction and perpendicular of the seam?
Yes,
So, sir,
it is well established that when you do layer by layer and line by line, you will get some directionality. But you know, the biggest thing you need to focus on in additive manufacturing is to produce complex shapes. Okay, you know, you can't do certain shapes at all without additive manufacturing. So if you have a re-entrant angle, okay, so just to give you an example, if you look at a chess piece for a castle, right? If you can make that by additive manufacturing, then you can have all the doors, windows inside the castle, this staircase and so on, which you cannot actually make by any other method. So the uniqueness of additive manufacturing is that you can produce very complex shapes. And General Electric, for example, has an entire factory making combustor components for the jet engine using additive manufacturing.
thank you, sir.
Anyone else?
So there are three raised hands I can see.
Yeah.
Abhinesh Barma, Ritesh Tandon, and I do not know, Joshua wants to again take a chance.
Yeah. Hello,
Abhinesh
hello,
Verma
sir.
had already asked, no? Or,
No, sir.
yeah,
First time.
Verma.
Yeah. Good
okay,
afternoon,
go ahead.
Bhadeshia, sir.
Yeah.
Sir, I am a PhD scholar in IIT Ropar. So I am just about to start my research work on nanostructured bainite. So till now, what I have found in industry that we have current problems with bainite are big to get a big size component, and second one is weldability, and third one we can say it is ductility. The problem that I have studied in the literature. So what, according to you, the problems there still exist which need a focus to research in near future?
Yeah. So you know, I explained earlier that I don't like to predict the future nor try to change the past. Okay, so you have to actually think about this yourself and decide on the most exciting area by reading and seeing what's done and then sparking ideas. So it's not for me to predict the future.
Okay, sir. Fine.
There's someone called
Yes,
AV.
sir, I can ask a question.
Okay.
Yeah.
Yeah.
Just I wanted to ask a question which is like most common for every undergrad fresher student. That how can we explore this department of metallurgy in a best possible way, sir? As we are like we have just stepped inside it. How can we, sir? Yeah. Thank you.
So I'm not sure I fully understand.
I think he wanted to know, or your suggestion, that being a sophomore, how can he find what are the interesting areas in the Department of Metallurgical Engineering?
The only way to discover new ideas, well, there are two ways. One is you need to do a huge amount of reading of what has already been done, and you will find discrepancies. Okay, so as soon as you do a literature review, you will find discrepancies and problems, and then you will also find misinterpretations, and that really sparks your imagination. Okay, so the best way is not to ask somebody on what ideas I should work on, because top-led research usually is boring. Okay, so you find your own ideas by doing a great deal of reading, finding discrepancies. You will automatically find discrepancies. Now, this is hard work, all right? It's hard work. But think about it like this, that if you do a really good job, then you can write it up and publish a literature review. Yeah? And you will very quickly know more than your professor.
True. Yeah. Are there any? Yeah, Jayasuriya, you wanted to say something?
Can I just go? Sir, I'm really sorry that you have been talking for very long.
No problem.
Just curious. The question of epsilon carbide and omega transformation that somebody asked sometimes back, I do agree with the fact that carbide chemistry and its structure and transformation in steel is really a very unexplored area. Similarly, nowadays there are confusions about zeta phase also, like it is a really carbide or a carbonitride or things like that. So I really do not want to comment on omega transformations in carbides. But do you think this omega transformations, which has been reported in other alloy systems, like in zirconium or in titanium, or even before that, the high pressure omega transformation, they're all artifacts of electron diffraction?
Not at all. Not at all.
Yeah,
So,
because I can refer to the work done by Steve Sass. There they clearly shown that the dovetail pattern keeps on moving on 1/3, 2/3 over the reciprocal lattice vector. So they cannot be so mathematical, isn't it?
no, but I think I'm not saying that omega transformation doesn't exist. In titanium, for example, it's very common if you have a certain amount of alloying. But it is a very strange transformation that, if you look at the set of planes, 2 planes out of 3 will collapse into each other. Okay?
Exactly.
So it causes an enormous change in symmetry and properties. And it's very well established in titanium alloys in particular. And I forget the name of who was the director of BARC.
S. Banerjee. Professor S. Banerjee. Dr. S. Banerjee.
He did work on that as well.
Yeah. So the omega transformation which has been observed in zirconium, titanium, they're pretty much well established.
Totally. Yeah.
Totally. All right. Thank you, sir.
So, do we take do we continue, or shall we call it now?
Well, first of all, let me apologize for the interruptions, which when you give me the video, I'll edit those out. Okay. But it was a pleasure and really nice to see the familiar faces as well. So thank you very much.
Thank you.
Thank you.
I think there may be some formal vote of thanks, but I would like to express my sincere thanks to you for having given such an excellent talk. And you have shown as an innovator, not only just an innovator, out of box thinking. The emphasis that you have laid is very important, that it is always important to think out of box, conventional thinking. You may be aware or may not be, but one of my senior colleagues, late Professor Ramchandra Rao, used to tell me when I was a PhD student with him, he used to say, Shastri, don't read too much. Think about, and then you will get new ideas.
Okay, that's another way.
Yeah. So I'm sure the youngsters as well as all the senior colleagues, researchers have enjoyed Professor Bhadeshia's talk, and we are extremely thankful to you, sir, for having spared your time. And Jesuri, is there any formal, is some student saying about it?
Yes, students will be saying about that.
Okay.
So actually, I would now like to invite Manna sir, as he was the person who could like arrange this lecture for us. So I'd like to invite Manna sir to give a vote of thanks.
Manna, you are mute. Unmute. Please unmute.
Okay, sorry. So dear participants, on behalf of Department of Metallurgical Engineering, IIT BHU, and on Nation 2021, Metallurgy Society, IIT BHU, IIM Varanasi chapter, and Student Affiliate chapter IIM Varanasi, I extend my hearty thanks to Professor Sir HKDH Bhadeshia for kindly agreeing and delivering an outstanding lecture on breaking paradigm in steel technologies. He has blessed our students by his kind words and knowledge, as well as many other students all over the country. For information of students, as he has mentioned, I visited his laboratory in 2011 and spent about 3 months. I have many interactions with him, and he has visited us during NMD ATM 2013. On behalf of department, I would like to request Sir Bhadeshia if he can find some time later to visit our department in future. I also thank all other participants for patiently enjoying his lecture. I thank my beloved teacher, Professor G.V.S. Shastri, for nicely conducting this session. Thank you all.
Thank you,
Thank you, Professor.
Okay.
Thank you, Harry.
Professor Shastri, you are on mute. Sir, you are, please unmute, sir.
Professor has left.
Oh, he has left, sir.
Yeah.
Oh, he left. Yeah, it was muted, so that's why maybe he couldn't hear.
Yeah, I think now recording can be stopped so that we can say chit chat if anybody wants.
I would like to